Thanks everyone for joining us today for our webinar, Capitalizing on Class 4 Power in Optical LAN Applications. We're excited to have great speakers with us today from Tel Labs and Panduit to talk about Optical LAN and a new Class 4 power solution and how it can work in Optical LAN applications. Kicking us off today is John Hoover, Marketing Director for Tel Labs. John, go ahead and take it away.
Thank you very much. And my portion of this presentation is going to focus on the challenges of implementing smart buildings and even smart campuses. So there's about 5 different challenges that people are going to hit when they're designing and implementing these networks. And if we just go ahead and get into it, you'll see that the first one that comes up is scale and reach. I mean, that's logical. The number, the capacity, the spread of Internet of Things devices within a smart building and across the campus is growing exponentially. So these networks typically have a hard time keeping up with that load. It's a constant challenge. And then there's security aspect, all the multitude of these connected devices. It just increases the corporate attack surface and it makes these smart buildings vulnerable to attacks. So ensuring a strict security while the data is in transit and at rest is crucial. Next up, reliability, because bad things happen when the network goes down. And these smart buildings often are made up of the security endpoints as well. So ensuring that you have redundancy and failover mechanisms is crucial to avoid any disruption in the critical services, along with, let's say, e-commerce. And then top of mind right now is sustainability. And it is getting to the IT staff, and they must address issues like the energy usage and the cooling impacts and all of the introductions of plastics and PVCs and electronic waste that just grows over time and certainly hurts the embodied and operational carbon impacts. In fact, it can be measured in tons, the impact of the network. Last, and why we are here today is the power management. This is a constant question that comes up, and managing all the IoT endpoints and their power utilization, power over Ethernet, and the backup powering. It's critical to the smooth operation of this smart building. So ensuring safe, reliable, strong powering is absolutely critical to these IT smart buildings, and especially as they grow across one building or across the whole campus. So the good news is that there are elements that can help, and that's what we're here to talk about. So when we talk about a passive optical LAN, and then we start talking about implementing class 4 fault managed power, when it comes to the scale and reach of these devices, now we have a design in place that can handle it. I mean, these devices are growing by the hundreds, if not the thousands. And with a fiber-based network in place, you can have 5 times the density, and even in some places, you could have 128 times the Ethernet density across a single mode fiber cabling. And what's even better about this network design is the reach. So 100 times the reach over a fiber-based network. And today, if you install it, it's ready for 10 gig, 40 gigs, and even 100 gig speeds. And then when we look at security, what an optical LAN can provide is eliminating known network security gaps. And these are actually the command line interfaces, the management interfaces. These switches are full functioning devices. So if you can pull those old Ethernet switches out and replace them with an optical LAN solution, you can actually do a better job of reducing the corporate attack surface. And it's a great architecture for zero trust architecture. Now let's look at the reliability of it. In these optical LANs, they come from the carrier world. They have better stability. They have industry-leading uptime. And when you have that, when you implement that, you can actually lower your operational costs, reduce human error. And when you're reducing human error, actually you're improving security as well, because we all know that humans are one of the greatest reasons for taking out a network, and they're actually one of the greatest reasons for a security breach. Now, with this fiber network in place, you start talking about sustainability, and you're reducing the embodied and operational carbon impact. Embodied carbon is what you put in the building. It's the material, it's the plastics, it's the PVCs. And then from an operational carbon input, that's the energy savings and the reduction in AC. So all of this can have a measured improvement in the metric tons, and it can really aid for those companies going to net zero initiatives. And now we get to talk about powering innovations, and class 4 fault managed power is a great innovation that finally unleashes these optical LANs, allows them to actually push the distances that they can, and really enables these smart buildings and the ability to power them over a powering system that has greater capacity over longer distance and in a safe manner. So my next slide just hopefully tees up the conversation today. In the past, when we were designing these passive optical LAN networks, you could locally power the optical line terminals and the optical network terminals. Passive optical splitters were always passive, so no power needed there. But nonetheless, with local powering, we could stretch 12 miles. And let me be clear, off those optical network terminals, those deliver the PoE, the power over Ethernet, down to the IoT devices. So then we started getting a little bit more sophisticated with our designs, and we used class 2 remote powering. And this could be done in a centralized or distributed architecture. But nonetheless, it had about this 2,000-foot range that you could push the DC power out to these ONTs. You could start using composite cabling, composite single-mode fiber cabling, and that was nice. And then the ONTs themselves then delivered the PoE down to the end devices. But here's the exciting part. Now we have class 4 fault managed power. And with this design, now we can push these optical network terminals out over a mile. Now they may directly connect an ONT, or they may go to a class 2 system that can have better density down to multiple ONTs. But nonetheless, once again, to be clear, it's the ONTs that deliver that PoE down to the end IoT devices in a smart building. So hopefully with that, I've given you some of the challenges and some of the places where optical LANs help. Now I'd like to turn it over to my colleague, Ian Merrill, who will give you a little more insight into the actual passive optical LAN networks.
Thank you, John. Hi, everyone. My name's Ian Merrill. I'm the Enterprise Account Executive for Tel Labs in the Northeast and the Mid-Atlantic. And over the next few moments, I'm going to give you a bird's eye overview of the passive optical LAN solution. So we're going to start with a side-by-side comparison of a traditional Ethernet network and an optical LAN solution. So what you're looking at right now should look very familiar to everyone. This is the way people have been building their networks for decades. It's tried and true, it's accepted, and this is the way people have been doing it for a long time. So you have your main switch in the data center, you have fiber running up the riser, connecting various access switches that are going to be under lock and key in a closet. And then from there in the horizontal, you have point-to-point connectivity using copper cable. And that copper cable is going to reside on a ladder rack or a cable tray like you see there. And you can go up to 300 feet and connect all those devices. Passive optical LAN looks a little bit different. So this is a multi-point topology that consists of 4 main components. Starting in the lower right-hand corner in the main data center, we have our optical line terminal, or OLT. The OLT is the brains of the system. It's the single controller for the entire system. It's where all the information is stored. It connects us to the core network, and it also houses our network nodes, or what we call optical LAN ports. So each of those optical LAN ports has a single fiber interface, and from there, we're going to have those fibers go up the riser, and those fibers are going to connect to the next component in the system, which is represented by those three triangles you see there. Those are the optical splitters. The optical splitters can split the signal up to 64 times in an XGS-PON or 10G network, or up to 32 times in a GPON or 1G network. So from there, we're going to continue down the horizontal, still using fiber, and those fibers are going to reside in those J-hooks that you see there. So we're definitely saving space there. And those fibers are going to uplink our next component, which is the optical network terminals, or ONTs. This is our fiber to copper media converter where we're connecting the devices from. So we have a lot of different flavors of ONTs depending on the network design with various fiber counts. So on that first floor there, you see an example of an in-wall design where they're actually recessed into the wall in a single gang plate, look a lot like an electrical outlet. Or we can have a zone scenario like you see in the floor above that in the middle, where you have ONTs and zone enclosures, could be in the ceiling. Or we have a rack mount option like you see up above. And the fourth element is the actual software that gets downloaded onto the OLT. We use Panorama software. So we're taking thousands of Ethernet devices, and because we have single mode fiber and optical splitters, we can take those thousands of devices and run them back to a single centralized location in the main data center. Because we're using single mode fiber, which is effective up to 18 miles, if you're in a campus environment, you can extend your network over your entire campus out of the same OLT. So Optical LAN is a simple and easy to manage system that scales easily and inexpensively, is secure enough for the federal government, offers carrier grade reliability, and it's good for the environment. It cuts down on energy usage and energy costs. So the simplicity of the passive optical LAN system starts at the head end where the OLT is located. So that's where everything is managed. And that's one thing that it's a big differentiator from your traditional Ethernet, where every individual switch needs to be managed separately. It takes a lot of time, a lot of effort, and a lot of personnel to do that. So in this scenario with a passive optical LAN, everything is managed through a single pane of glass from the OLT. So that saves a lot of time and money. And if you have a staff of 6 people and everybody chips in with managing moves, adds, and changes on a daily basis, you can reduce that number to maybe 1 or 2 people that are going to move or manage your daily moves, adds, and changes. And that opens up time for the rest of your staff to do other things that are more productive, developing new applications, preparing for future technologies, and in some cases, you could even have them specialize in certain aspects of the network. The scalability is easy because that's driven by the single mode fiber. So what does that mean? When it comes time to refresh your network, you very seldom have to rip and replace cable, which is a timely and costly event that has a negative impact on the landfill. Single mode fiber can stay in place for decades, and it can adjust to any upgrades that you do in your system. The other thing you can do because of fiber is mix and match 1 gig and 10 gig transmissions through the same fiber infrastructure. One of the things driving 10 gig right now is supporting Wi-Fi 6 and soon to be Wi-Fi 7. So we have a lot of customers up there that want to stay at 1 gig, but they want to go to 10 gig for that application. So what that entails over on the right side, the downstream side where the ONTs are located, that entails taking out your 1 gig ONT, replacing it with a multi-rate 10 gig capable ONT, and then punching that serial number to the new ONT into the software at the OLT. At the OLT side, it's just a matter of replacing your 1 gig optic with 10 gig optics, and then you're in business. So if you have 1 gig and 10 gig, you're going to run a 1 gig fiber to that little device that's just to the left of the middle there. It looks like an old plug and play data center module. That's an optical combiner. So you run a 1 gig connection there, then you run a 10 gig connection up there, and then that device combines the signals and sends all that traffic down the same strand of fiber using different wavelengths downstream and upstream to make sure that those transmissions don't interfere with each other. Anyone you talk to about passive optical LAN that is hearing about passive optical LAN for the first time is going to ask you about security. And some folks might even doubt how secure passive optical LAN is. But the reality of it is it's not only secure, but it's very secure. And the most obvious advantage is the fiber itself, because it's made out of glass. It's very difficult, if not impossible, to tap into that to try to steal information. The only console in this entire system is at the OLT, and that's the only component that needs to be under lock and key for that reason. The console port is where you're going to get physical access to the network. So if you have any bad actors or intruders walking around in your building, that is the only place where they could get that physical access to the network and start wreaking havoc on your system. The ONTs themselves, while they're super valuable to us, they're practically useless for an intruder, because if they try to get into the network that way, there's no console port. There's also no IP address to protect with the ONTs. They store no information, absolutely useless to an intruder. There's no way to get into the system that way. And coupled with our advanced security features in our software, also everything is AES 128 encrypted. So that's the advanced encryption standard 128. That is a 128-bit key that scrambles a signal, and it has a 60-second churning key, which further scrambles the signal. This is a very, very secure system. In terms of reliability, one thing to note here is that passive optical LAN is derived from the carrier world, or more specifically, Verizon Fios. So what does that mean? The carriers are held to strict standards as far as availability, because this is availability for the general public. So the strict standards, more specifically, are 5 nines reliability. So from day one, as soon as you install this system, you're getting 5 nines reliability, which equates to about 5 hours or less of downtime a year. There are other ways you can build up more reliability, more levels of redundancy using our advanced availability software. So you can do port protection, which if you have a smaller deployment and a smaller ONT, maybe you only have one line card with ports, you can do port-to-port PON protection. If you're using a larger ONT, you can simply use card-to-card protection, and then build your way up to the most robust reliability and redundancy standard, which is dual chassis redundancy. So what that means is you have a second OLT. It's going to be diversely located with diverse fiber paths. And if you look at the bottom, and we're going to call that second column, bottom of the page, we're going to call that OLTA. OLTA is doing all the transmitting and receiving. And the OLT above it we'll call OLTB. Through the software, that OLT does not transmit and receive just yet. It's simply watching the traffic from the OLT, the main OLT, between the OLT and the downstream ONTs. And if anything goes wrong with a fiber or a port or a card, instantaneously, those transmissions are going to fail over to the secondary ONT or OLT. And that happens in a matter of a few seconds or less. And that gives you 6 nines reliability. That equates to about 30 seconds a year of downtime. And finally, passive optical LAN is very environmentally friendly. And we do this a few different ways, starting with the physical footprint. We reduce the physical footprint significantly, and we do it throughout the entire network, starting in the main data center where the OLT is located. We can achieve up to 4 times the Ethernet port density out of one rack with the OLT and the single mode fiber. So we're saving a ton of space in that location alone. When it comes to the closets or the telecom rooms, we're saving space there because in a lot of instances, we can completely eliminate the need for a closet, depending on the design. If we do need a closet design, we still don't need as much air conditioning in there because our OLTs and ONTs have wide temperature ranges and do not require anywhere near the power and cooling that a traditional system requires. And then the pathways, since we're using fiber in the horizontal, we're using 4-port ONTs a lot of times, we're significantly reducing the pathway usage, and we can often use J-hooks and not have a need for ladder racks or cable trays. So when it comes to energy, typically in a building, we'll see anywhere from 30 to 50% energy savings. But the larger the deployment, typically that percentage of savings increases with it. So I'm going to use Sandia National Labs as an example of this. That is a massive deployment that we did maybe 8 or 9 years ago, and it's a big federal facility out in nowhere, New Mexico. So we have 17 or so OLTs and thousands of ONTs. And 5 years after they did the first install, Sandia National Labs reported back to us 65% energy savings. And in terms of dollars and cents, that equated to about $20 million of operational savings after their first 5 years of operation. Also, when we're bringing ONTs closer to the edge, closer to the device, we get more efficient use of PoE. Passive optical LAN also has a long cable life and a long shelf life. So typically we'll see 8 to 10 years before you see a need to refresh an optical LAN system. So fewer actual refreshes, much fewer rip and replace events, and that single mode infrastructure is going to support any future versions of optical LAN that come down the pipe. And lastly, back in August, Tel Labs introduced the first passive optical LAN carbon reduction calculator for enterprise network connectivity, where you can actually put in your information and do an estimated comparison of optical LAN versus a traditional Ethernet network, and you can see very closely how much or how many metric tons of carbon you can save by installing a passive optical LAN network. And with that, I'm going to hand it over to Mahmoud, where he'll talk us through fault managed power.
Thank you, Ian. Hello, I'm Mahmoud Ibrahim, the commercial lead at Panduit, in charge of bringing to market this new innovation called Fault Managed Power System, or as we call it, Panduit's FMPS. It is the first and currently only Class 4 listed system in the market. John did a great job earlier of talking a little bit about Class 4 and how it works. I'm going to take the time today to first touch on what Class 4 really means, what the standards and what the code says about it, and then we'll talk a little bit about the Panduit product, the applications, and how it fits into passive optical LAN. I'd like to start off by first explaining what the existing classes of power are. So traditionally in the NEC code or NFPA 70, we have 3 classes of power, class 1, 2, and 3. Class 1, we're all familiar with it. It has no power limit. You can do up to 600 volts. And that's basically what's running in our buildings today. It requires an electrician to install it, and that cable needs to be running in conduit for safety reasons. You also have class 2, which is limited to 100 watts and 60 volts. Those are also known as power limited circuits. The beauty of class 2 is that it's safe. It's considered a low voltage installation, and you don't need to be running it in conduit because it's safe from a shock hazard perspective and a fire initiation perspective. Class 3, not widely deployed, but it's limited to 100 watts and 150 volts. It still requires an electrician to install it. Now we have class 4. And what it is, it's basically been recently introduced in the National Electrical Code. The best way to describe class 4, it's combining the best of both worlds, class 1 and 2, where we're now able to make the delivery of higher voltages safe. In the standard, under class 4, they're referencing 2 specific standards. UL 1400-1 is specific to class 4 listed systems, and UL 1400-2 is specific to class 4 listed cables. The systems are covered under Article 726, and cables are covered under Article 722. Class 4 is not like Class 2, which was considered power limited circuits. It is, however, what's called an energy limited circuit. So we have the ability now to push up to 450 volts across the copper cable. And by energy limited, it means we're trying to minimize the amount of energy that goes into a fault when the fault occurs. So for instance, a fault like me touching the copper conductors while there's high voltage, A class 4 listed system needs to be able to monitor, detect that touch, and turn power off almost instantly. I will be exposed to that power, but very limited energy, and that's what we're trying to minimize so it doesn't cause any harm to me. The beauty of that now is if you're able to design a class 4 listed system that complies with these standards, that now means that you can treat these systems as almost as a class 2 installation. So you can treat it as a low voltage installation. So now if we take a quick look at the comparing class 1, 2, and 4, as I mentioned, class 1, high voltage levels, high power levels, requires an electrician, needs to be running in conduit. You're typically using large wire gauges, anywhere from 10 to 12 gauge, and has no limit on the distance. Class 2, limited to 60 volts and 100 watts per copper pair. The beauty, again, it's a low voltage installation, no conduit, but as John mentioned earlier, there is limitations in distance. Once you go beyond 200 or 300 meters or try to push more than 200 to 300 watts at the edge, it becomes very inefficient because you basically have to pull multiple copper pairs to get to that distance or that much power. Now you have class 4, which allows you to push up to 450 volts. You can have really high power levels. You will see with the Panduit system, we can deliver up to 600 watts per copper pair. Again, the nice thing about class 4 now is it's considered safe, so can be used as a low voltage installation. So basically, if you think of an optical LAN installation, you're running fiber. Now that same contractor can be pulling the copper alongside the fiber or even using hybrid cable to do so. We'll talk a little bit more about that later. With class 4, because you're pushing high voltage, now you can leverage much thinner copper conductors. So typically you'll see 16 or 18 gauge can really get you up to 2 kilometers away. And as I mentioned, long range. So you'd see the Panduit system can actually push power beyond 2 kilometers. We are on a journey. Class 4 is new in the NEC 2023 code. And this work did start back in 2021, where UL started and formed a group to look at the power delivery standards. The 1400-2 standard was published in January of 2022. It was adopted into the code of 2023. And just or about a year ago, in December of 2022, that's when the 1400-1 standard was published. And just recently, last year, Panduit was able to bring into the market the first class 4 listed system. I say we're on a journey because the code adoption of and the adoption of class 4 in general will really affect the adoption of this technology. Right now, we have 7 states across the US that have adopted the new code and so are making plans for class 4. There are also 12 states underway looking into adopting the 2023 code. This is going to help the adoption of class 4 in general. Now let's take a closer look at class 4 and what an end-to-end deployment looks like. You'll always be looking at a class 4 transmitter and a class 4 receiver. Those are governed by the standard UL 1400-1. Connected by a class 4 cable, which is governed by UL 1400-2. This is an end-to-end class 4 deployment. And again, the system is constantly looking for faults across the copper pair. If any of the faults that are listed in the standards occur, the system needs to turn power off almost instantly. If that fault clears, it can be self-healing and restart that circuit again. Again, if you're able to do this, now you can have a class 4 listed deployment, which makes it easy for you to leverage a low voltage installation. I like to compare this to what we know today for hazard mitigation methods. So class 4, as I mentioned, is safe, but how safe is it? So today we're familiar with GFI outlets and AFI outlets. What I'm showing you in this table really are the 2 types of hazards that are commonly we worry about for electrical circuits. It's either shock or fire. I'm also showing you the different types of faults that can occur that need to be tested for with class 4 systems. You can see that GFI outlets are good for just one type of fault. AFI outlets do a little bit better and include arc faults. But now if you look at class 4, it's covering all of these faults listed. And so one can say that the delivery or distribution of class 4 power is safer than what we have running in our buildings today. Just to touch on Cable, I mentioned there is class 4 cable, and this table here, I'm showing you some of the main specs in the standard, in the 1400-2 standard. The main one to point out is insulation rating, because now we can push up to 450 volts across the copper cable. These cables need to be rated to a minimum of 450 volts. The standard does, however, keep it wide open in terms of the gauge size, the solid or stranded, single or multiple copper pairs in one. The standard also covers different types of cable construction. You'll see general plenum, riser, and general purpose cables. You'll see indoor-outdoor options, or even hybrid options. So you'll see class 4 hybrid, which has fiber and copper in the same cable. The last 2 points I like to mention here are, you'll see that these cables are typically twisted because you'll typically see multiple pairs in one, and so it makes it much easier from an installation perspective. And then termination is going to be very vendor specific, but you'll see with the Panduit system, we're using screw Phoenix connectors throughout, which are very common in the industry. There are class 4 cables out there today from multiple vendors. And what I'm showing you here are basically some of the variations that you can find out. There is anywhere from 14 to 18 gauge, 2 to 8 pair. There's plenum and indoor-outdoor options. There's shielded, unshielded, copper only, and hybrid. That little chart is also just to give you an idea of the sizes of these cables. Right there in the middle is going to be what you'll see typically inside buildings, and specifically with the Panduit product. We have a 3-pair 16 gauge, not a 4-pair. So it's slightly smaller than this 0.4 inches. Now let's get into the Panduit product and the value of the fault managed power system, how it works, and the different parts and pieces to put together. So Panduit's fault managed power system, again, is the first class 4 system in the market. This is a significant achievement because it basically means we've tested and complied to the UL 1400-1 standard. As we speak today, we are currently the only system that has gone through this process. What we're giving you is a new way to distribute power where and when you need it. You can almost think of this as an extension cord that you can run safely up to 2 kilometers away. So you can really imagine what kind of applications can be at the end of that. You're getting significant power. We talked about 600 watts per copper pair over long distances up to 2 kilometers away. Safely, because we comply with the latest UL 1400-1 standard, and efficiently, because now we're pushing high voltage. I like to just touch on this, and I already mentioned it. There is a lot of buzz out there on class 4, but it's really key to understand who has class 4 listed systems. As I mentioned, there are some class 4 listed cables out there, and if you go to the UL Product IQ website, you'll be able to find out which class 4 cables and which class 4 systems are out there. And as we stand today, again, Panduit has the only class 4 listed product or system in the market. How our system works. So typically you'll have a transmitter that's sitting in the head end or the MDF closet of your building. It takes in AC and converts that AC into what we call pulse current, or you can consider this your class 4 circuit, being pushed over a class 4 cable up to 2 kilometers away out to the receiver. The receiver can be wall mounted or rack mounted. It will take class 4 power in and convert that to 48 volt DC to power end devices. Like I mentioned before, each of the copper pairs coming out of the transmitter need to be monitoring for these faults that are in the 1400-1 standard. If any of these channels see a fault, they need to turn power off almost instantly. If that fault clears, our system is self-healing and will just restart that circuit again. If a fault occurs in a single pair, it does not affect the other nearby pairs. So if you look at the system in the front here, there are 9 channels. If one of these channels experiences a fault, it's only that fault that actually has the fault that will turn off. The other channels will continue running. This is what our product offering looks like. It's basically made up of 4 parts and a cable. You have the transmitter, which is a 1RU unit. It comes with a network management card that you can connect to your local network. And through an IP address, you can basically log on to the system, do monitoring and control. In terms of monitoring, you can monitor voltage, current, temperature, how much power is being consumed, and how much power capacity you have left. You can also do control. You can actually control and turn devices on and off centrally. You can also pull data out of our system using SNMP version 2, version 3, or using REST APIs. The transmitter chassis, again, is a 1RU rack mountable unit. It has 3 slots in the back for power supply units to plug in. It has up to 9 channels in the front, or these transmitter modules can slide in. This is what a power supply unit looks like. It comes with its own cord, makes it a very IT-friendly installation at the head end side. The transmitter modules are hot swappable. Those are basically what are doing the magic. They're sending out that high voltage that's being pulsed, and they're the ones that are monitoring for any of the faults if they occur. They push up to 600 watts of power. Those 3 pieces kind of sit together in the head end, and then you have the receiver, which is going to be at the far end, taking in pulse current or class 4 power and converting it to 48 volt DC. As I mentioned, this receiver is well mountable, but you can also mount it on a rack. It has 3 input channels on the bottom. Each input channel would connect to a single transmitter module. So the distance and the gauge that you use will really dictate how much power you have available at the receiver. Just as a rule of thumb, if you're using a single transmitter module connected to a receiver, you can expect using 16 gauge at 400 meters, about 530 watts out of the receiver. If you aggregate and add 3 channels, connect 3 channels to the receiver, you will get the full 1600 watt capacity. That is using 16 gauge at 400 meters. If your gauge size changes or the distance changes, the capacity will always change. This is also can be handled through design, and Panduit offers free design services to help with figuring out how much of the FMP product you need to size it up for your project. The last piece of the system is the cable. Panduit has a class 4 cable that is a 3-pair 16 gauge, and it goes along with the topology of our receiver, which has 3 input channels. Why even consider this product? What you're getting with the Panduit Fault Managed Power System, or FMPS, are 2 facts, and those are really giving you all the benefits. You're getting safe high voltage, and you're also getting centralized power. Safe high voltage is what allows you to install this as a low voltage installation and allows you to deliver a lot of power over long distance. So it makes it a fast and easy way to install using less copper cable and no conduit. This is all associated with savings from day 1 of installation. The bigger benefit comes with the centralized architecture. Now, with a centralized source of power from our transmitter, delivering power up to 2 kilometers away to your devices, you can centrally back up the system with 1 UPS rather than having to have UPSs distributed all over your building that needs to be managed. You can also maintain the system. You can troubleshoot it by basically being able to control and turn devices on and off remotely. It's also scalable, makes it very easy to make moves, adds, and changes. If day 1 you needed just 500 watts at the edge, you only use a single transmitter channel. If you need more power in the future, you simply slide in a new card into our transmitter, and now you have more power at the edge. The applications for this are endless in our opinion, and what I'm showing you here are just some of the applications that have been spoken about already in the field. We focused a lot on in-building wireless and also smart building applications, whether that's using network architecture or PON. This is just an idea of what the applications are, but in our opinion, again, sky's the limit, and I think you as users will come up with where else to use this technology. But now let's take a look at how this fits into a smart building application. What I'm showing you here is the typical network architecture, where you have a core or aggregator switch that is sitting in the MDF or head end. Alongside with it, you can find your transmitter backed up by a central UPS. And now you can have your copper and fiber running in the same pathways out to the IDF closet, potentially powering a switch at the edge. This is one way to do it. But now how you can leverage this in an optical LAN installation, very similar architecture. You can now go very long distance with our cable along with your fiber up to 2 kilometers away. So this is example number 1. You'll have your OLT and your transmitters sitting in the same head end, maybe backed up by a centralized UPS. You can again send your copper and fiber out in the same pathways, no conduit, or even in the same cable to your remote location, where in this case, you're trying to power the ONT directly. So I'm showing you here a Panduit class 4 receiver that takes that class 4 in and then converts it to 48 volt DC to power the ONT. And from there, the ONT can provide PoE out to your devices. People often ask, how does the copper and fiber live together? And I'm just showing you here one way of how you can terminate these two together now in the same location. Another way to do this is by using a class 2 distribution at the edge. So very similar architecture at the head end. You still have your class 4 copper and fiber going out. The class 4 copper is going to the receiver. And in this case, the receiver is powering a class 2 power distribution system. So this can be your long distance up to 2 kilometers away, and you can let the class 2 power distribution handle the last couple of 100 meters to the ONTs. You could have your passive optical splitter in the same zone enclosure or in a completely separate location. But basically what we're saying, you're sending fiber and a copper pair going out to this ONT. That concludes my presentation on Panduit's fault managed power in class 4. The product is out today, and as I mentioned, we do offer free design services. So if you have a project in mind, how this fits into a passive optical LAN project, we're happy to work with you as well as the Tel Labs team to answer any of your questions. Thank you for your attendance today.